Hello and welcome. This is my latest acquisition. These are two Fluke 8375A digital multimeters, 5.5 digit, Nixie tube readout, which I love. They were made in the mid-70s, and surprisingly they just turned on and worked more or less. They definitely have a bunch of issues. This top one in particular has some really flaky selector switches. You can see the range flickering because that switch hasn't settled. Gonna have to clean those up. I managed to find the manual for these, so I have schematics and part numbers and everything. Once I get these cleaned up and working, I'm going to give them serial data output so I can log the readings on my computer and make graphs and stuff. These are the most precise, stable, and potentially accurate meters I have, and they come with 90-day and 1-year specs for stability. So I'm really excited to look at subtle, long-term phenomena with these. Let's take a look at this one. Last calibrated in May of '97. Turns on and zeros pretty well. There's a DC zero adjustment on the front panel, which I guess means that you kind of have to access that fairly often. I've got the inputs shorted together right now, so 0.1 volt range, 8 or 9 microvolts, a little bit of noise. Let's see how the filter does. It's got a really nice active filter. So you saw a spike in the reading as soon as I turned the filter on because it was already charged and took a minute to settle. There is supposed to be an indicator light that tells you that the filter is on. That doesn't seem to be lighting up. It works. And I guess it's not really settling. The manual specifies a warm-up time of 1 hour before you actually try to use the thing. This has a true RMS AC meter. This thing also has a built-in quick self-test function. So volts DC should be around 20 volts within a tenth. That's a bit off, but not too bad. Switching it over to volts AC. Should show 13 plus or minus 2 volts. And that looks good. Let's see what ohms does. Okay, it's not within spec, but it's not too far off either. Not bad for 45 years old. This sample rate light, too, that should be flashing every time the reading updates. And kind of give these selector switches a thorough cleaning inside and out. I just love this metal shield with holes drilled in it for the calibration adjustments. The blue case you just saw me remove is the dust cover, just some flimsy plastic. This metal cover underneath is what shields the electronics from interference while you're turning the knobs. This meter is sensitive enough to respond to stray electric fields from a technician's hand, even when wearing an ESD strap. Here we go. Yeah, of course. This should be disassembled enough to get at those switches. And the light that was supposed to flash every time we took a sample. This is a tiny incandescent bulb. So that's probably burned out. Let's see if it's too difficult to replace that with an LED and a resistor or something. And look at these Nixies. Digits are about ½ inch tall. The function annunciator. I think there's a set of LEDs, one for each cutout in here, inside this little box. And the switches. We're going to take these completely apart and clean the contacts. I've got this thing powered up with the case off, which is kind of dangerous, but I know what I'm doing. So I went to check out this sample rate indicator light, and the first thing I did was try to measure the resistance across it in the circuit. You usually can't test components when they're inside the circuit because the test current from the meter could pass through other components. In this case, though, the transistor should be an open circuit when it's off, so the meter's test current has nowhere to go but through the bulb. And if not, I know there's something wrong with the transistor. So across the bulb I measured 500 ohms, and after cutting it out of the circuit, I measured an open circuit. So the bulb is burned out. But that transistor is probably bad because it's not an open circuit. That 500 ohms shouldn't be there. You can see the problem when I put this LED in the bulb's place. The 500 ohm short is keeping the LED on all the time, and it just gets a little brighter when the transistor turns on. So here's the voltage at TP2. 0 to 5 volt pulse. I mean, it's not particularly pretty, but this should totally be triggering that transistor when it's on and turning it off when it's low. This is a good signal. Transistor Q36 is my suspect here. Of course, I can't access it without taking the whole motherboard out, so time to tear the whole thing apart. RMS converter assembly. Ohms converter. Buffer assembly. Active filter. Logic assembly back here, and the A to D system right here. This is the range delay. And the power supply. And here's a complete DMM from 1974. I love how everything is discrete and visible. VDC input from the front panel jacks enters this buffer card, which either amplifies or divides the input voltage to the system native 10 volt level. The buffer sends its 10 volt signal to the active filter, which is a bypassable 4-pole filter at about 4 Hz. The filter sends its output to the A to D card. The logic card generates timing signals and saves the result from each digit of A to D conversion on these quad flip-flops. Those timing signals are also repeated at a few dozen hertz and used to drive the multiplexed Nixie tubes. BCD from the logic card is decoded by this 10-line decoder driver chip here. Simple and visible. I love it. Okay, plan B. That's what I need. Okay, I got my alcohol bath here for the contacts. They're still inside. You can't just push these back. There's a little latching tab you have to hit. There. That comes out. Here's one contact. Here's the other. Now these two don't have the same locking bar because they're not mutually exclusive. They're just toggles. They do have this little latch pin in here. Used to be held on with one of these clips. Clean the pins too, why not? So the manual wants me to desolder this edge card connector to get at the contacts for the back of these 3 switches. While I usually admire that flavor of extra, I think I'm going to skip that this time. So inside of this thing, there are a bunch of these little metal plates that mesh with the little plastic cams that ensure that only one of these can be pressed in at a time. Ha! Take that, manual. After cleaning, the contacts must be recoated with a thin coat of grease. Use Ricon 2 EP grease or equivalent. I spent hours down this rabbit hole, and I learned about fretting corrosion, so now you will too. It's basically a feedback loop of friction and oxidation. So, almost any metal exposed to air is going to oxidize. Corrosion-resistant metals just oxidize in a way that forms a protective layer over the deeper metal. A little bit of it does corrode, but it stops quickly. Aluminum doesn't rust because aluminum oxide is really hard. A layer of aluminum oxide forms that's a few atoms thick, and then the deeper metal is shielded. Iron oxide, on the other hand, is soft and kind of flakes off on its own, so iron just rusts into oblivion over time. Gold is actually one of the only metals that won't oxidize on contact with air, which is why you see it used on contacts so much. But you can't use it in switches because it's so soft it just scrapes away pretty quick. Anyway, since oxides are generally non-conductive, to make an electrical contact you need to break through that oxide with some force or friction. Now you have metal-to-metal contact, so your switch is connected and current can flow. But as soon as you move the contacts again, that metal you just exposed is going to oxidize. So every time you push the button, you're breaking old oxide and exposing new metal so it can oxidize. Over time, you turn this whole piece of metal into oxide and scrape it off. And after a while, your whole contact is dust. If you coat the metal surfaces in grease, you prevent the air from touching the metal directly, so a lot less oxide forms and less of the contact gets scraped off every swipe. Less air, less oxygen, less oxide, less problem. Grease is an insulator too, but it generally doesn't cause problems in switches because metal is pretty jagged on a microscopic level, and the grease flows out of the way of the little jagged edges poking each other. Okay, what kind of grease do I buy? Hey, maybe I can get some new old stock Rikon. Some 40-year-old grease. Nah, that's stupid. I didn't know there was a national lubricating grease institute. Additives for extreme pressure. The 2 in 2 EP means it's got the consistency of peanut butter. There's no extreme pressure. Why the hell is that grease specified? Oh my god, the forums are just condescending neckbeards arguing about WD-40. What year is it? I've found a few people who swear by silicone dielectric grease, and I have some, so I'm going to try that. These selectors are back together. These two are still just momentary without that little locking pin. This old Tony has a really good video about latching mechanisms. Those two pins in there. And now these things latch. These bottom switches are the same. They're mounted upside down. So I'm going to have to stick these in blind. Beautiful. Okay, the switches at long last are back together. Let's look at Q36, the transistor for the sample rate light that we were having trouble with. This is a 2N3904, which is not the part that's called out by the manual. I've hooked up the extracted Q36 up to a really simple LED driver circuit. This is exactly what's present in the circuit board, and unfortunately it looks like this thing actually works. But that doesn't necessarily mean it was working perfectly. I guess occasionally I've seen a flaky part start behaving after it's exposed to soldering heat. Might have been some kind of flaky bond wire inside the package. Also could have been, I'm not sure what the finish is on this circuit board. It looks like it might be tin based, and that's exactly the kind of thing that tin whiskers can cause. It's an unexplained sort of moderate impedance short. And that would have disappeared as soon as I touched the iron to it. Forgive my technique here. Remove the old incandescent and install the new red LED with a little resistor under that heat shrink. Now the little annunciator display panel thing. This was socketed. I was not expecting that. Circuit board with some simple wiring back here. Now, in the schematics, in the manual, there's supposed to be 8 LEDs inside this thing. I wonder what we're going to find. 7 incandescent bulbs. I guess there's no millivolt option on this meter. I'm going to attach 5 volts. I guess I'll just replace all those with LEDs then. So this plastic housing is, I think the term is heat staking, where they just cut holes in the circuit board and had pieces of the plastic that went kind of through and then melted them and pushed them down, kind of like a plastic rivet. So I'm going to try to cut them off, glue it back. April 12th, 73. Color should I replace them with? I've got an amber and a red, which are, I think, my two best options. Here's the lens from that indicator. No clear winner. How about with the diffuser? I think I like red better. Yeah. Functional test. 4, 5, 6, 7. Good. Yeah, this thing just plugs in right here. These resistors are 39 ohms, and those are what drive those now LEDs. I'd be driving like 80 milliamps through each LED, which will kill them in short order. So I gotta replace those. .220 ohm resistors. Okay, we're all back together and turned back on. The improved annunciator is working great. I figured out the issue with this sample light staying on most of the time and just getting a little bit brighter. Turns out there was an undocumented, not present in the schematic, extra like preheat resistor, sort of bypassing the transistor there. And I think that was there to kind of improve the response time on the incandescent lamp, kind of keep it warm while it's off. I saw the exact same thing on the overrange light, and the sample light and the overrange light are the only lights in the system that aren't Nixies that need to respond in a pretty quick manner. So that must be it. Pretty sure anyway. Maybe it improves their service life, keeping them warm. They don't cool all the way down, so the temperature differential isn't too huge. I think I must have a later version of the manual. This device differs from the schematics in the manual by quite a lot, even though the model's the same. This must be a really early version. I was about to shoot a wrap-up clip about how I ran into almost no issues with this thing, and it just needed some maintenance. And all of a sudden, it stopped taking samples. It's kind of frozen at this reading. But stopped sampling when I started playing with the external sample command setting, which is the full counterclockwise little switch on that pot. And there we go. So yeah, I'm just not going to turn this knob all the way back. Problem solved. I should get a replacement for that pot, but it's going to be hard to find an exact replacement with the right kind of switch built in, and I don't intend to ever use the external sample command. I'm just going to call this good. Okay, look at this. Negative 75. positive 50. Negative 70. All these boards are connected together with these edge card connectors. I wonder if they get flaky when you shake them. I'm going to try to torque them by lifting the back end of these cards one by one and see if I can find the source of the issue. Lift and drop the back a little bit. That's changing a little bit. Oh, that changed a lot. That might be it. Yeah, nothing going on with the filter card. And the A to D and logic cards. Oh, yeah, I don't know what I was expecting there. But, it can induce some glitches, but not those offsets. I'm going to try to tap these relays and see if the relays are bad. Tiny bit. This one. Ooh. That one might be it. It only flips when I tap the body of the relay, not the circuit board. So I'm pretty sure it's this relay and not the edge card connector. Unfortunately, I can't find a good replacement for that relay, and replacing it with a modern relay is going to be a huge amount of work, so I think I'll just live with it. Typically, signal relays like this have gold-plated contacts, and I'm guessing that over years of clicking on and off, the gold has worn away, and whatever base metal the contacts are made of has fretting corrosion. The contact resistance now changes a little bit every time it moves, just like in the switches earlier. I can't find a good replacement for that relay, and replacing it with a modern relay is going to be a huge amount of work, so I think I'll just live with it. Okay, so I didn't touch the calibration on this thing, aside from zeroing it and adjusting the bias current. It looks like it's tracking my modern Fluke meter at around 0.1%, which is so impressive. I'm kind of speechless. Those calibration stickers hadn't been lifted in 23 years. These things were sitting on a rack in a movie prop store. It's just unreal. I don't have the equipment I'd need to calibrate this thing correctly, and it doesn't come cheap. I think I'm mostly just going to leave it alone and use the precision for relative measurements without really trusting the accuracy to anything better than about 1%. I'm really happy with this thing. I got really lucky finding something so old with no real issues, just kind of needed some cleaning. In the next video, I'll talk calibration and do some circuit analysis. There's some pretty fun stuff in here. And maybe I'll make another video for the serial data output stuff. Thanks for watching.